All right, so in the last lecture, we introduced the idea of feedback control. It's a very broad lecture, just introducing the idea of the feedback structure and kind of exploring what the capabilities of feedback control are. Um, what we did was we outlined the basic unity feedback control structure and did some examples as to how this control structure might apply. We did an example about cruise control, HVAC systems, um, the Segway scooter, and maybe a couple of other examples. Um, and so we outlined the basic idea of feedback control, and then we actually took a step back. Uh, we focused on the plant transfer function, which is one component of the feedback control loop. And the reason that we're focusing in on the plant block first is because, well, we need to understand the nature of the dynamic system before we can be comfortable closing the loop around it to try and control it. And if you recall, the plant represents the dynamic system that you are trying to in fact control. So it's the real life dynamical system that you want to manipulate into behaving in some ideal manner. Okay, so the plant is a representation of, say, the automobile sitting in the driveway, or it's a representation of the robotic arm that's in the laboratory setting. Right? It's the actual mechanical, electrical, dynamic system that you're actually trying to control. And the idea is, well, I sort of left you with this picture last lecture. There's kind of several different ways to represent those system dynamics. On the one hand, you have the actual physical system, which is the real life system. And through some intuition, if you deal with a certain system long enough, you have some intuition as to how it will behave. For example, we took the scenario of being in an automobile and kind of flooring the gas at a constant known input. And intuitively, we kind of knew that the output velocity would start at zero, kind of accelerate and taper off until you reach a constant terminal velocity. Okay, so that was intuition about this particular real life system, but we took it a step further and we asked the question, well, can we actually capture those dynamics in some mathematical fashion? And the answer was yes. Okay, so the, the big takeaway from the first lecture is that you can actually take some real life dynamic system and you can actually model it, right? So through the process of modeling, we can get generally one or more differential equations of motion. And those equations of motion um, mathematically capture the dynamics of that particular system. So it's, in some sense, it's an equivalent representation of the real life system, only we have it in the mathematical world. Okay, so differential equations, those exist in the time domain. And if you look back through the notes, there are several more examples that I didn't do in the lecture where we go through that process of modeling. Okay, so the process is generally the same for all mechanical systems. One way to model them is to basically do a force analysis where you analyze all the external forces. And then you apply Newton's second law. So sum of the forces equals mass times acceleration, and that can be done in the linear realm or the rotational kind of realm. Okay, so that's kind of where we left. And then at the very end of the lecture, I hinted that there's yet another way to express dynamic systems. And in addition to the differential equation, there's something called the transfer function. Okay, the transfer function is something you would have picked up in an earlier system dynamics course, but we're going to review it here nonetheless. Okay, and the whole point is that the differential equation, the transfer function, are both supposed to represent the actual real life system dynamics, and so we can put all three of these boxes kind of on the same plane because they all represent the same thing. Um, the key here is, well, how do we actually get the transfer function? Well, the transfer function is obtained through something called the Laplace transform. Okay, so the Laplace transform takes you basically from the time domain into the so-called S domain, or sometimes called the Laplace domain. Okay, so this Laplace transform is actually just a mathematical operation. And I'll write it down once. Laplace transform, that's shorthand for transform. I'll write it down once just to show you what it looks like. But basically, we're never going to use this integral. And I'll show you why in just a minute. Okay, so if you look at the input side, the right-hand side of this transform, pretty much you see you've got your time domain input, right? So some function of time, you plug it in, evaluate this integral, and then what you get on the right-hand side is the Laplace domain equivalent of that same time function. So this is a transform in the sense that it takes something in the time domain and transforms it into something into the S domain. Okay. This is the fundamental definition of the Laplace transform. It's a mathematical equation. That's really all it is. However, in the context of dynamic systems, it allows us to represent our differential equations, which are in the time domain, and take them into the S domain. So the actual mechanism for getting a transfer function is to take the Laplace transform of both sides of the differential equations. There are a number of reasons why you might want to express the dynamics of a system in the S domain rather than in the time domain. And probably the most obvious one is that the math for dealing with Laplace transforms, the math for dealing with the transfer functions can often be much simpler than dealing with differential equations. I mean, at this point, you've all taken a differential equations course, and you realize there's a whole course in mathematics dedicated to just learning how to solve these types of differential equations. So in general, differential equations are kind of tedious and cumbersome to work with. So the transfer function is another option for you to use so that you can analyze the same systems. And it turns out that the math is relatively straightforward. Another reason is that, well, based on that assumption that the math is a little bit easier to deal with the transfer function in the S domain, several tools for both design and analysis have been developed for the dynamic system in the S domain. So we have analysis tools and control design tools available, but only if we express the system as a transfer function. Right? We don't have those same tools available for the differential equations in the time domain. Okay, so that's some motivation as to why we're going to go into this in-depth review on how to get a transfer function. Okay. The other thing is there's something called the inverse Laplace. So if you have a function in the S domain, you can actually inverse Laplace it and take it back into the time domain. Okay, so you can jump back and forth between domains. And the only reason I'm bringing that up is because we are actually going to use those two strategies to do some interesting things. Okay, so the Laplace transform in general is not, it's not specific to control systems, but in control systems we use it as a tool to simplify our analysis and design process. And because of that, I only want you to be able to do four primary things regarding the Laplace transform. There's a lot more stuff that this integral is capable of doing, but for our purposes, these are the four things I would like you to be able to do. First and foremost, I would like you to be able to derive a transfer function given the ODE. Right? So once you model the real life system, you get a differential equation or set of ODEs that describe that system. From there, I would also like you to be able to derive the corresponding transfer function. In other words, go from the time domain into the S domain. The other thing I want you to be able to do is to take a function in the S domain, and purely mathematically, I'd like you to take the inverse Laplace of that to return to the time domain. Okay, so basically I want you to be able to go from the time domain to the S domain, and then from the S domain back to the time domain, which allows us to sort of jump back and forth between the time and the S domain. The reason I want you to be able to do that is because if you can do these two things, which admittedly are very dry and pretty just mathematical, there's nothing super exciting about them, but if you can do these two things, then you actually have the capability of doing more interesting things. The two that I want you to know about is that if you can go back and forth between the time and the S domain, well, then you actually have the ability to solve differential equations. Okay, so you don't have to use the same tools that you use in your differential equations course. You can actually use the Laplace method to solve differential equations, which is very powerful, especially given the fact that now we understand that differential equations can actually express dynamic system behavior. Okay, so that's one thing. You'll be able to solve ODEs. And perhaps even more importantly, as it pertains to this class, you'll be able to solve what's called a forced response. A forced response is essentially if you have a transfer function and you know what input you want to apply, right? Essentially the input is called a forcing function, which propagates through the system dynamics and produces an output. Well, you can actually compute that output if you know the transfer function and you know the input that you want to apply. And that's very powerful. That is basically, in essence, that's the idea of simulation. Okay, so if you have a model for your system and you want to see what happens if you apply some specific known input, you don't actually have to go to the lab and apply that input. If your model is good enough, you can just run a simulation and see what the output would look like. And that's basically the idea of computing a forced response. And so if you can do these first top two checkboxes, then you can actually do the bottom two checkboxes, and it becomes a more useful tool, the Laplace transform, once you can do all four of these things. Okay, so for the purposes of this class, we just want to be able to check off all four of these boxes. All right. Okay, so with that said, I do have to admit that this lecture is rather dry. There's nothing super interesting about this lecture. It's very mathematical. We're just going to go down the line and check off all four of these boxes to make sure you understand fully how to use the Laplace transform. Okay. All right. Let's handle the first. Let's handle the first box, the first checkbox. If we want to derive a transfer function, it would probably help. It'd probably be helpful to define what a transfer function actually is. I mean, I explained that it's another way to represent the dynamic system, but I haven't actually stated what it is mathematically. Okay, so the transfer function definition goes like this. Basically, we reserve capital letters for S-domain functions and lowercase letters for time domain functions. And fundamentally, a general picture of an input-output relationship would look like this. Okay, so h of s is some transfer function that represents some dynamic system. U of t, well, that's some known input. Okay, so if you're gonna get into a car and floor the gas pedal, U of t is a constant value. If you're gonna get into the car and sort of undulate the gas pedal sinusoidally, then U of t is a sine function, right? So U of t can basically be any function that is the input to that system. And then Y of t, of course, is the resulting output for that particular system. So in the case, okay, let's just say in the case of the vehicle, like if h of s represents vehicle velocity, if U of t looks like this, then we already know that Y of t is going to look something like this, right? So those are your inputs and your outputs. Now the definition for the transfer function itself goes like this. The transfer function h of s is defined to be, it's actually the Laplace transform of the output divided by the Laplace transform of the input. Like so. Okay, so adopting this notation that the Laplace transform of a time function, we just say that's the capital letter of that same signal. So big Y of s represents the Laplace transform of little y of t. That's the notation that we're going to use. And so for that, with that definition, then the denominator here is just capital U of s. Okay, so the Laplace transform definition is sorry, one more time. The transfer function definition is that it's the Laplace transform of the output divided by the Laplace transform of the input, with one special caveat. We're going to assume zero initial conditions. Okay, and that's very critical because the Laplace transform aims to capture the pure dynamic behavior of that system, right? It doesn't concern itself with whether it was already moving or if there was some other initial condition involved. Okay, so the definition is the Laplace transform of the output over the input, assuming zero initial conditions. Okay, so there's your definition of the Laplace transform. Now, what I might say is, okay, in the notes there are several examples which basically illustrate why you don't use this, right? Right? This is the definition of the Laplace transform after all, this kind of funky looking integral. Okay, but, and I'm not going to do this example all the way, I'm just going to show you why we prefer not to use that integral. And it's because the math gets really tricky really quickly. Okay, so let's just say for the moment, that we have a scenario where we've got some unknown transfer function, but we know the input and we know the output. So u of t, y of t. Let's say u of t is equal to a constant value 1. Y of t is equal to some different constant value a. Okay. In order to figure out the transfer function h of s, which is our goal here, we would need to take the Laplace transform of this and divide it by the Laplace transform of that. Okay, so let's just start with u of t is equal to 1. How do we take the Laplace transform of a constant value? Well, if we were going to use the integral definition, it would look something like this. Big U of s is equal to the integral from 0 to infinity of 1, which is the time function, times e to the minus st dt. And we'd have to evaluate this integral. Okay, so what we want is the derivative of the inner function present inside of the integral. And that's easy. We can put it there as long as we compensate outside. Okay, so we want that minus s to be there, and we can put that minus s there as long as we compensate by a negative 1 over s out front. And we've got e to the minus st dt. Now taking this integral is relatively straightforward. It's basically just e to the minus st. We've got e to the minus st, and we've got the limits of integration on the outside here. And all of this boils down to minus 1 over s. E to the negative infinity, that's 0, minus e to the 0, that's 1. So we get a negative 1 here, and we basically get that big U of s is equal to 1 over s. Okay, that is for the most basic, essentially, time function that exists, a constant value of time. Requires all of this integration just to get the s-domain function for that. And then we have to repeat all of that for the output. Okay. The point I'm trying to make here is that this is very tedious. This is extremely tedious, right? We don't want to have to do this every time we derive a transfer function. Furthermore, let's just take it one step further. Let's just suppose f of t is not a constant, but it's a constant times time. So it's just a ramp function. This is probably the second simplest time function that exists. Okay, if we want to take the Laplace transform of this using the integral method, well, again, we've got to plug into the integral. So the time function here is b times t, and then we've got e to the minus s dt. Remember, I'm just plugging in f of t into the basic definition of the integral. Now immediately we see that this becomes a much more tricky integral. Okay, we need to actually do integration by parts, which means we need to let u equal to bt. Generally, you let u equal the thing that gets simpler when you take its derivative. In this case, we have du would be equal to b dt, and then dv would be the other stuff, which is e to the minus st dt, which makes v equal to minus 1 over s e to the minus st. And then we've got to plug into our integration by parts, which fundamentally looks like this. AB u dv is equal to, it's uv evaluated at the limits minus v minus the integral of v du. And then we'd plug all this stuff into that. And basically you can see that this becomes a page or two worth of integral calculus just to take the Laplace transform of the second most simple time function that pretty much exists. Okay, so all of this to say we're not going to ever use the basic definition, right? We don't want to actually use the integral definition of the Laplace transform to find our transfer functions. Okay, so what we do instead, turns out that at some point somebody tabulated all of these Laplace transforms. So some poor grad student somewhere probably sat down and really did all of these integrals for, some Laplace tables have hundreds of elements in them. Okay, and essentially we want to just use that work for our purposes here. We don't want to actually reinvent the wheel here. Okay, so what I mean by that is you have available to you, I've supplied you with a pretty decent Laplace table, but if you look online or in your textbook, there are hundreds of different versions of this in greater detail or less detail. And basically what, the core of any Laplace table is basically two columns. You've got a time function column and its corresponding S-domain function. Okay, so the two that we've done so far, or at least the one that we've done so far and the second one that we looked at, exist here. Okay, so for some time function a, this is some constant function. And in our case, we did the example of a is equal to 1. And we found that the Laplace domain version of that is 1 over s, or a over s in this case. So that checks out. And that's just the very first element. If we carry through with this integral here, with f of t is equal to b times t, we should find that the Laplace transform of bt would be equal to b over s squared. Okay, and that's indeed what we would get through a lot of painful calculus. Okay, the point I'm trying to make once more is let's just use the table whenever we can. Okay, so all of this to say, let's never do those terrible integrals, and let's just use the Laplace table. Okay, in the notes, in the lecture notes that I've posted, for whatever reason, I felt compelled to do several of these examples just to really show you how much how inconvenient it really is. It's really no fun to do these integrals. Okay. Point is, okay, we're just going to use a Laplace table, but we do have our definition of what the transfer function is. Okay, that's still the main point of this section of the lectures. We're still trying to derive a transfer function given a differential equation, which still means, based on the definition of the transfer function, that we need to take the Laplace of the output and divide it by the Laplace of the input. Okay. Okay. All right. So all of this to say, let's not use the integral, the Laplace integral. Let's try and use the Laplace table as much as possible. Okay. All right. Let's finally get into an example here where we can apply this. Okay. So from last time, from the first lecture, we had this example. Okay, and I'm going to still put it in this sort of picture here, just to keep everything, consistent here. I want to show you how this first example we did fits into the same picture here. Okay, so we had the real system. It was a vehicle, and we wanted to model the velocity dynamics, right? So we had some input that was the thrust provided by the engine, and the output was the forward velocity of the vehicle. Through the modeling process, which we did in the last lecture, we actually derived the differential equation. which looked like v dot of t was equal to minus b over m v plus 1 over m u. Right? That was the actual differential equation that governs the vehicle velocity dynamics. And all we're going to try and do now is generate the transfer function, which in this case is going to be, okay, if the output is v and the input is u, the transfer function we're going to be looking for is a ratio of v of s over u of s. That's the transfer function that we want. Okay? And the way we get there is to take, you start with the differential equation, and you can actually derive this ratio without knowing the inputs and outputs. You can actually start with the differential equation, take the Laplace transform of both sides, and simply solve for this ratio, independent of any input or specific input or specific output. Okay, so starting with this differential equation, let's take the Laplace of both sides of it. We'll start with the right-hand side because taking the Laplace transform of the right-hand side of this equation is pretty straightforward. Minus b over m, that's a scalar constant. Okay, and scalar constants are allowed to just go down to the Laplace domain. Okay, so there's nothing you have to do with the scalar constant. V of t, little v of t, the Laplace transform of little v of t, we're going to just apply the notation for that, which is basically to say the Laplace transform of little v of t is big V of s. Right? So that's all you've got to do for that part of it. And then 1 over m, that's another scalar constant, but u of t is a function of time. The Laplace transform of little u of t becomes big U of s. So that's the Laplace transform of the right-hand side of this equation. It's very straightforward. The Laplace transform of the left side implies that we need to take the Laplace transform of a time derivative of the function. Okay, so that sounds daunting at first, and it could be if we apply the integral definition of the Laplace transform, but if we just refer to the Laplace table, most of them will have an element somewhere that deals with the time derivative of f of t. For this table, it's down here. See, df dt, that's essentially f dot. And the Laplace transform of f dot has the form of s times capital F of s minus the initial condition. Okay? So what we have here is, since we're dealing with the variable v, the Laplace transform of v dot is s big V of s minus little v of 0, the initial condition. So all of this is the Laplace transform of v dot of t. Now here's the other thing, and this is really the only time we can do this is when we're deriving the transfer function from the ODE. Remember, the definition of the transfer function assumes 0 initial conditions. So we can actually take this one step further and zero out that initial condition. Okay? Once you take the Laplace transform of both sides of the differential equation, you should be left with only stuff in the s domain. There should be no more time variables floating around in your equation. If that's the case, which it is here, then it's simply a matter of algebraically solving for this ratio. Okay? In other words, s v of s is equal to minus b over m v of s plus 1 over m u of s. We just have to solve for v over u. Okay? So what that means is let's move this to the other side and factor. So we get s plus b over m times big V of s. All of that equals 1 over m times u of s. And then from here, divide both sides by big U of s and divide both sides by this whole parenthetical. And what we get is the ratio v of s over u of s equals 1 over m s plus b over m. Okay, so if we distribute this m in, finally we get v of s over u of s is equal to 1 over ms plus b. And we can give this ratio a name. We can call that P, the plant dynamics, right? So bringing it full circle back to the original unity feedback control structure, the P, right, that P block, which is part of that unity feedback structure, it represents the system dynamics, and it's always equal to the Laplace of the output over the Laplace of the input. Okay, so this is essentially how you derive a transfer function from an ODE. The steps are take the Laplace transform of both sides of the ODE, zero out your initial conditions, and then solve for the ratio that you're interested in. In this case, it's V over U. Okay, and what that allows us to do is to basically fill in this last step where we have the transfer function representation of the dynamic system. Okay, so it's hard to believe for now if this is the first time you're seeing this, but this vehicle system, right, the velocity dynamics associated with that vehicle are exactly captured by this differential equation here. And it also turns out that this is another equivalent way to represent that same system. It's just in a different domain. Okay, so the time domain is just different from the S domain. All right. These are all equivalent descriptions of the same system dynamics. I can't stress that enough. Those are all equivalent, and it's hard to wrap your head around that at first, but you just have to understand that you're working in a different domain, so the function's going to look different. All right. Okay, so for any differential equation that you come across, you can always apply this method to solve for the transfer function. And what that allows us to do is to check off this first box. Okay. The next one, this one's the next checkbox is the worst one. Okay, let's just start there. It's not as simple to go from the S domain to the time domain as it is to go from the time domain into the S domain. And part of the reason for that is to go from the S domain to the time domain, we want to, again, use the Laplace table as often as possible. But the S domain functions are not always given in forms that look like stuff on the Laplace table. That's fundamentally why this case is a little bit more tricky. And in order to overcome that, we sort of break it down into a couple of different scenarios. Break it down into a couple of different scenarios. What we want to do is go from the S domain back to the time domain. This basically requires taking the inverse Laplace, right? This is the inverse Laplace operator, going from the S domain back to the time domain. And to handle this case, different textbooks will lay this out differently, but the way that I found is the most transparent and straightforward is to break it down into 4 different cases. Okay, so the first case really isn't even a case. It's really 3 cases plus 1 trivial case. Case 1 we'll call the trivial case. And the reason I'm calling this trivial is because the steps for taking the inverse Laplace of a case 1 scenario is just to use the Laplace table. Right? You just want to use the Laplace table. Okay, so what I mean by that is if I ask you to take the inverse Laplace of, let's say, f of s, where f of s is equal to 1 over s plus 2, I'm basically asking you to find what is little f of t. What is the time domain representation of f of s equals 1 over s plus 2? Right? So you'd have to take, if you didn't have the Laplace table, you'd have to take the inverse Laplace, you'd have to apply the inverse Laplace integral to get that, and that's just as tedious, if not worse, than the forward Laplace transform integral. Okay. Again, this is a trivial case because this right here exists on the Laplace table, right? So something of this form 1 over s plus 2 exists on the Laplace table. And you can see it right here. Okay, so 1 over s plus a, that's the form of the S domain function. The corresponding time function is just e to the minus whatever a is times t. Okay, that's it. This is a trivial case. There's no math to show. You just use the table. Okay, so in one step, I can say that little f of t is equal to e to the minus this thing, t. Okay, so it's simply a matter of using the Laplace table. That's the trivial case. That's the ideal scenario. We would love for all of our cases to be case 1 because then you could just use the Laplace table. Okay. Sometimes that's not going to be the case. Case 2, we're going to call this distinct real roots. Distinct real roots, well, roots of what? What I mean by distinct real roots is you look at the S-domain function that's given. And first of all, you want to rule out that it's a case 1 by looking on the Laplace table. Okay, so here's some transfer function or S-domain function, 3 over s times s plus 2. Okay, now let's suppose that the Laplace transform that I gave you doesn't have this element on it. Right? There's nothing of the form a constant over s times s plus a different constant. Okay, it turns out that some Laplace tables actually have this, but this is just for illustration. Okay, if you cannot locate the S-domain function that's given on your Laplace table, well, then you're not a case 1 anymore. So you're some other case. And in this scenario, we're in a case 2, distinct real roots, because, again, if you look at the roots of this S-domain function, which is to say the values of s that make the denominator equal to 0, so what you see here is that the roots are, of course, s equals 0 and negative 2. Those are the roots of this S-domain function. Well, those are both real values, and they're not the same value. They're distinct from one another. So 0 and negative 2, that is what puts us in this classification of distinct real roots. Okay, so anytime you have a scenario like this, you should look at the denominator of the S-domain function to classify what case it is. Okay, what you do in this case, and in fact, in case 2, 3, and 4, in all subsequent cases, the whole point is basically to reduce it to a case 1 scenario, right? So you're always trying to manipulate the original function, make this look like stuff that is on the Laplace table, right? If this doesn't exist on your Laplace table, let's just like mush it around and like reorganize it so that it does look like stuff on Laplace table, okay? And the easiest way to do that is to use something called a partial fraction decomposition. Okay, it's not the most fun thing to do. It's very tedious. It's somewhat dry. It's very mechanical in its application, but it does serve a useful purpose. It basically breaks this thing down into the sum of a bunch of simpler things. Okay. The way it works for distinct real roots is you look at each one of these roots and each one gets a term. Right? So something over s, but instead of a product, it becomes a sum. So this is partial fraction expansion for distinct real roots. Okay, partial fraction expansion. So we're just going to rewrite the original function in a different way. That's all we're going to do. The only thing is we don't know what these numerator coefficients are just yet. Okay, so partial fraction expansion for distinct real roots says that there are some coefficients a and b such that this equation will be true. It'll be a valid equation. But before we get into the steps of how to find a and b, let's just assume that we know a and b. Okay, so let's just say a is 1 and b is 6 or whatever. If we know a and b, can we then take the inverse Laplace of this stuff? Right? That's the question. The answer is yes, right? Because I already know what the inverse Laplace of a over s is, right? If you look at the Laplace table, that's just this guy right here. The inverse Laplace of a over s is a. The inverse Laplace of a constant over s plus another constant, well, we just looked at that one in the previous example. Okay, so 1 over s plus a, the inverse Laplace of that is e to the minus at. Okay, so it's comforting to know that once I do find a and b, my problem is basically done because I'll just look at the Laplace table. Okay, the rest of the problem is basically just, well, how do I find a and b? Okay, how do I find a and b? And I'm going to give you two tools to find the coefficients of the partial fraction expansion. Case 2 will highlight the first one, which is using the cover-up method. The cover-up method basically treats this whole thing as one big equation, and it manipulates it so that you can isolate either a or b. That's really all it is. The cover-up method is nothing more than algebraic manipulation. Okay, so the cover-up method says that 3 over s times s plus 2 equals a over s plus b over s plus 2. This is just an equation, which means we can do whatever we want to it as long as we do the same thing to both sides. So in this case, what we want to do is multiply both sides by s. Okay. What that allows us to do is to isolate the value a by itself. Okay. So on the right hand side, a over s times s, well, that's just a. Plus b over s plus 2 times s, that becomes b times s over s plus 2. And then on the left hand side, we just have 3 over s plus 2 since the s's cancel. Okay, so all I've done literally is just multiply both sides of the equation by s, but now recognizing that this is an equation of the variable s, I can evaluate it at any value that I want. So a strategic value that I might choose here would be s equals 0. And the reason I would suggest s equals 0 is that notice if I plug in s equals 0 to this s right here, this whole term goes away because you get a 0 in the numerator. Right? So b times 0 is 0, 0 over s plus 2, the whole thing is 0. Okay, but I need to evaluate this equation and plug in 0 everywhere I see s, and that leaves me with 3 over 0 plus 2 is equal to a by itself. Okay, so in this sense, I have covered up, quote unquote, this term over here by setting it equal to 0. So through the cover up method, I get a is equal to 3 over 2. To find b, okay, you do the exact same thing except you isolate b. Right? You multiply both sides of the equation not by s, but by s plus 2. And then you evaluate not at s equals 0, but at s equals negative 2. And you will see that that allows you to isolate the variable b. And once you isolate the variable b, you just evaluate to see that it becomes minus 3 over 2. So I encourage you to try that yourself. The full solution is in the notes if you want to refer to that. But this is how you apply the cover-up method for finding the coefficients a and b. Now you've gone through all this work to find these coefficients. Are you done with the problem? No, really you haven't even started, right? And that sounds kind of daunting to say, but really all I've done is rewrite the original s-domain function. So 3 over s times s plus 2 equals some constant a, which I now know is 3 halves over s, plus some other constant b over s plus 2. So this just becomes, right, so f of s originally was 3 over 2 times s plus, 3 over s times s plus 2. Another way to write that is 3 halves times 1 over s minus 3 halves times 1 over s plus 2. That's what our partial fraction expansion set up here. Right? So I found a and b, and I'm just rewriting it in this different way. Okay? So these two are equal. These are both equal to the original f of s function. Well, I can't take the inverse Laplace of this directly off the table, but I can take the inverse Laplace of this and this. Okay? So right away at this point, I said now you get to start the problem. That's kind of a misnomer because you're basically done. You've reduced the entire problem to a case 1 scenario, and now all you have to do is to take the inverse Laplace of these easy to find Laplace table entries. Okay, so scalar constants get to come down, so 3 halves. The inverse Laplace of 1 over s, just referring back to Laplace table, 1 over s, inverse Laplace of a over s is a. Okay, so inverse Laplace of 1 over s is 1. Minus 3 halves, another scalar constant, times the inverse Laplace of 1 over s plus 2. We just saw that one in the previous example. That's going to be e to the minus 2t. Okay, so e to the minus 2t. And when you're finished, you should be left with only stuff in the time domain. Right? So 3 halves minus 3 halves e to the minus 2t. That is the inverse Laplace of the original s-domain function. Okay, that's just case 2. Okay, so case 2 is when the s-domain function has distinct real roots. Well, we spent some time outlining the process for how to find the inverse Laplace of those kind of funky s-domain functions. Case 3 and case 4, they're a little bit more intricate, but they follow the same general process, which is basically to rewrite the s-domain function into a sum of a bunch of simpler things and then take the inverse Laplace of those simpler things. Okay, so that's case 2. Case 3 is when you have repeated real roots. Well, what does that look like? Repeated real roots of what? Remember, we're looking at the roots of the S-domain function. And in this example, we have several roots. Okay, so s times s plus 1 cubed. What is the inverse Laplace of 1 over s times s plus 1 cubed? I don't know. That's definitely not on any Laplace table that I've ever seen. Okay, so we need to basically rewrite this somehow so that it looks like a sum of a bunch of simpler things. Okay, so again, it's no surprise here, the way we're going to rewrite this is to use the partial fraction expansion. Okay, and the only reason case 3 gets its own case is because the partial fraction expansion is just a little bit different. Okay, so the partial fraction expansion for something with repeated real roots, it looks like this. Okay, so for the distinct root, which is s, and by the way, let's just be absolutely clear here. What are the roots of this S-domain function? Well, the roots are 0, right? They're also negative 1, but it's also negative 1 and another negative 1, right? This is a fourth order denominator, which means there should be 4 roots of this S-domain function. These are all real value, but 3 of them happen to be the same. So that's why this falls into a case 3 scenario. Okay, so that was just a little side note. The distinct real root always gets its own term, so that's just going to be a over s. And again, the thing that differentiates the repeated real roots case from the distinct real roots case is simply how you break it down in the partial fraction expansion. Okay, so the way it works is you've got the terminal power of 3. For repeated real roots, you need to have additional terms all the way up until that terminal power. What I mean by that is this. So you're going to have b over s plus 1 to the 1. That's one term. You're going to have c over s plus 1 squared. That's another term. And you're going to keep going until you get to this terminal power. So in this case, you're going to have d over s plus 1 cubed, and then that's how you know you're done, because the cubic was the terminal power. If I wanted to be cruel and say take the inverse Laplace of 1 over s plus s times s plus 1 to the 7th, that just means you're going to add 3 more terms. So e over s plus 1 to the 4th, and so on until you get to s plus 1 to the 7th in the denominator. I would never do that because that seems a little bit cruel, but that is fundamentally how you write the partial fraction expansion for repeated real roots. All right, so this is not a ton of fun, but we can apply the same principles to solving this inverse Laplace problem. Because notice, if we had A, B, C, and D, then it turns out that each and every one of these individual terms is actually on the Laplace table. So then taking the inverse Laplace transform is very simple. The whole tricky part from here is to figure out what A, B, and C, and D are. We need to find those coefficients. Okay. Now it turns out, unfortunately, the cover-up method that we used in case 2, you cannot use it to find all of the coefficients in this problem. It simply doesn't work. You can use a cover-up method to find A, and you can always use a cover-up method to find the coefficient on the terminal power. But for all these intermediate guys here, for all of these intermediate terms, B and C, you will find that if you try to use a cover-up method, you will not be able to algebraically isolate B or C. It's impossible to do. Okay, so the full example of how that happens is in the notes, but I encourage you to try it if you feel like you may be able to use a cover-up method to find B and C. You will find that, unfortunately, you cannot do that. Okay, so the distinct term and the terminal term you can get from cover-up, and so I'll just state what they are here. Cover-up method for A and D says that A is equal to 1 and D is equal to negative 1. That's by following the exact same process that we used in case 2, so I'm not going to go over that in detail here. However, to find B and C, we employ a secondary strategy. And this really doesn't have a name in any textbook, but it's outlined in several textbooks. So I'm calling it C, D, E, and C, or some of my students have referred to this as CDENC in the past. It seems to stick. I kind of like it. C, D, E, and C refers to a procedure, and it sort of takes you through the steps to use to find B and C, these intermediate coefficients. And it's basically a two-step process. The first thing you have to do is to get common denominators, or CD. Okay, well, common denominators of what? We're going to look at this thing here as one big equation, and we want to get a common denominator all the way across that equation. Okay, once we do that, then we equate numerator coefficients to solve for the unknown variables B and C. That's the two-step process behind CDINC. Okay, so let's do the first part, which is get common denominators. It's not fun, like I said. On the left-hand side, we have 1 over s times s plus 1 cubed. On the right-hand side, we have 4 terms. Okay, a over s, but if I want this common denominator, I need to multiply top and bottom by s plus 1 cubed. Okay, so I've got a common denominator on the a term. The b term, well, in the denominator, I have one term of s plus 1, but I need an s, so I'll multiply top and bottom by s, and I want s plus 1 cubed. I've already got 1, so I need to multiply top and bottom by s plus 1 squared, right? Okay, for c, I have 2 terms of s plus 1 in the denominator, so I need an s and just one additional term of s plus 1 in the numerator to get s plus 1 cubed in the denominator, like so. And then the last one is the d term, and in the denominator of the d term, I already have s plus 1 cubed. So all I have to do is multiply top and bottom by s. And now I've basically done the first part of C, D, E, and C, which is to get common denominators. At this point, if you've already used the cover-up method to find some of the coefficients, you can go ahead and plug those in. So I know that a is equal to 1, and I know that d is equal to negative 1. So I'm just going to plug those in now to keep things a little bit simpler later on. Okay. The CD part is done. We have to equate the numerator coefficients now. What that means is this big long equation has, every term has the same denominator, which means if the equation is to be true, well, then the numerators have to be equal too, right? And if the numerators are to be equal, that will allow us to solve for B and C. Unfortunately, what it means is we need to actually expand all of the polynomials in the numerators to see, to be able to equate the coefficients of the numerator polynomials. This is not fun. How many times have I said that in this lecture? Equating the numerator coefficients means that we need to expand, right, every term. Okay, so we need to expand s plus 1 cubed. S plus 1 cubed is, s cubed plus 3s squared plus 3s plus 1. And then we've got b times s plus 1 squared. We've got to FOIL that out. Cs squared plus cs is what we get when we expand this out. Then we have a negative s here. The point is to get in the numerator one big polynomial in s, and that's what we have to do. So that's what equating the numerator coefficient entails. Okay, so I will skip a couple of steps here, but just know that I'm basically expanding each one of these terms, right? I'll do one, for example. Okay, s plus 1 cubed, that's s cubed plus 3s squared plus 3s plus 1. Plus, in the numerator, I've got, bs times s plus 1 squared plus cs squared plus cs minus s. So eventually, if I expand everything in this numerator out, I get one big polynomial in s. That's the thing that I need to equate to the left-hand side numerator. Okay, so cleaning some of this stuff up, what I end up with, right? Notice that there's an s plus, there's a 1s cubed here, And I'm going to get a bs cubed here from this expansion. So that's why I get a b plus 1 s cubed. And then for the s squared terms, there's a whole bunch of them, right? There's a bunch of s squared terms. 3 plus 2b plus c s squared. And then there's a bunch of s to the 1 terms too. So 2 plus b plus c s plus 1. So there should be a 1 at the end of all of this because, let's see, there's the 1 here, right? So there's our 1. And this is the numerator of the right-hand side of this equation. Okay, so all of this can be divided by our common denominator, s times s plus 1 cubed. And then over here on the left-hand side, 1 over s times s plus 1 cubed. Okay, so these are said to be equal, which means our denominators are equal, which means we actually don't care about them. And so what this ultimately means is that the numerator on the left-hand side has to equal the numerator on the right-hand side. That's fundamentally what has to happen. All right. Now, it's kind of strange to look at, a third order polynomial in s equals 1 on the left-hand side. So I prefer to actually write this a slightly different way. I'd rather see this as 0s cubed plus 0s squared plus 0s plus 1 on the left-hand side. This is all equals 1. But now what you have is a third order polynomial equal to another third order polynomial. And now hopefully it's more apparent what we mean by equate the numerator coefficients, right? From this third order polynomial, we actually generate 4 equations and 4 unknowns. If you equate the s to the 0 term, here, you simply find that 1 equals 1. So not super useful, right? But if you equate, say, the s cubed term, you find that b plus 1 equals 0. Well, that's useful because now directly I can see that b is equal to negative 1. And so I've solved for the b coefficient using this equation. Okay, then the other two coefficients, or the other two coefficients should give me the same thing. 3 plus 2b plus c equals 0 should be the same thing as 2 plus b plus c equals 0. So I can use either one of those equations to solve for c, and I would find that c is equal to negative 1 as well. Okay, so this is the Seedenk method. It's getting common denominators across the equation and then equating the numerator coefficients to essentially produce several independent equations with the several unknowns that you have. And this will allow you to always solve for the partial fraction expansion coefficients. Okay, are we done with the problem? Not really. In fact, I'll say it again. Now we can actually start the problem. Okay? It's a terrible thing to say because we've just put in a bunch of work. But look, okay, this was the original function that we were trying to find the inverse Laplace. I know that there are some coefficients a, b, c, and d that exist such that this whole summation of terms on the right-hand side is equivalent. And I've just gone through the painstaking process to find all 4 coefficients. So I've got a, b, c, and d now. What I can do is basically just rewrite the original function. So a was 1, b was negative 1, c was negative 1, and d was negative 1. Okay, so I've all this work to simply rewrite the original S-domain function into a sum of a bunch of simpler things. Okay, but the payoff is coming because remember that each of these terms is right there on the Laplace table, right? So 1 over s plus 1 squared, for instance, that's right here. 1 over s plus a, the quantity squared, has the inverse Laplace of t times e to the minus at. And then there's 1 over s plus a cubed right there. So in one fell swoop, at this point, I can go straight to the answer. Little f of t should be equal to the inverse Laplace of 1 over s, which is 1, minus e to the minus t, minus t e to the minus t minus 1/2 t squared e to the minus t, which is the inverse Laplace of 1 over s plus 1 cubed. Okay, so this is your final answer. This is the inverse Laplace of the original S-domain function here, right? I know, it's getting pretty hairy now. Okay, so we're pretty deep into these 4 different cases for getting the inverse Laplace. Case 3, the one that we just did, that's by far the worst. Okay, case 4, it's actually not that bad. Case 4 follows the same principles as case 2 and case 3, but with one simple caveat, which is that the definition is different. Okay, so we've only been talking about real roots this whole time so far, okay? But there are cases where you have complex roots in the S-domain function. Okay, so let's look at an example of that. F of s is equal to, let's say it's 1 over s plus 1 times s squared plus 2s plus 2. Okay, so the roots of this S-domain function, well, there's 3 of them. One of them is real, right? So one of them is s equals minus 1, but 2 of them are complex. Okay, so anytime you have complex roots, that is what puts us into a case 4 category. And again, just like case 3, the only reason complex roots really gets its own special case is because the partial fraction expansion is just different, right? The way to express this thing as the sum of a bunch of simpler terms is different from the distinct real roots case and the repeated real roots case. Okay? The way this one works is, well, you always have the distinct real root gets its own term, so a over s plus 1. Plus, now here's the thing, if you have a second order denominator, right, s squared in the denominator, then you can write that term in the denominator, s squared plus 2s plus 2, but the numerator becomes a first order polynomial, so 1 degree less in the numerator. So some coefficient times s plus some other coefficient. So bs plus c is a first order polynomial. That becomes a numerator for the quadratic or complex case. Okay, that's the whole reason that case 4 gets its own scenario, is because the partial fraction expansion is just a little bit different. Okay, from here, everything is the same. Everything is the same. Okay, all we're trying to do is find a, b, and c so that we can use the Laplace table to take the inverse Laplace of these much simpler terms. Okay, so let's see. Let's just do this one all the way out. So the distinct real root is always straightforward. By the cover-up method, you can get that a is equal to 1. That's easy. You just multiply both sides of this equation by s plus 1, evaluate at -1, and you'll zero out or cover up the big complicated term on the right. And you'll just evaluate that a is equal to 1. For b and c, again, you're going to find that if you try to use a cover-up method for these quadratic terms where you have complex roots, you can't isolate b or c by themselves. It's impossible. So this necessitates the Seedenk method. And in this case, it's actually not that tricky. The case 3 example was way more tedious. That's probably the most tedious thing that I'll ever give you. But if you notice, okay, so we want to use C, D, E, and C on this example. This is our common denominator here. To get that common denominator on the a term, I'd have to multiply top and bottom by the quadratic. Okay, so I'll have 1 over the common denominator is equal to a times s squared plus 2s plus 2 over that same common denominator. And then the bs plus c term, well, I've got the quadratic in the denominator here. To get the common denominator, I have to multiply top and bottom by s plus 1. And that would give me the common denominator. So this one's way simpler than the last example because expanding this numerator is not that tricky at all. I get as squared plus 2as plus 2a plus, and then just FOIL this out, I get bs squared plus c plus b s plus c. Right? That's just that's the expansion of this this product here, and all of that equals 1. Or I'd rather write it as 0s squared plus 0s plus 1 equals, and then I'm going to combine all the like terms here. So I get a plus b s squared plus 2a plus c plus b s as the middle term. And then I get plus 2a plus c as the third term. I think that should be right. That should be right. Yeah. And the thing is, I've already found that a is equal to 1. So actually, anywhere I see a, I can just replace it with the 1, right? I might as well just do that because I've already done the work to use the cover-up method. Okay? And then some students, after they do this enough times, they realize, well, wait, you don't actually have to use the cover-up method first at all. If you find that you're in a case where eventually you will need to use C, D, E, and C anyways, you could actually just skip the cover-up method, because ultimately what you get down here is you've produced 3 equations, right? I'm going to equate all of these. I'm going to equate all of these polynomial terms, and so a s squared polynomial gives me 3 equations, and I've got 3 unknowns, a, b, and c. So you could actually use just the seeding method without using the cover-up method if you prefer. I always find that's a little bit easier just to use the cover-up method to get some of them out of the way. Then the math becomes a little bit more straightforward when you're doing the seeding method. Nonetheless, it's up to you, right? So I've gone through the trouble of finding a using the cover-up method, so I plugged it in right away. And what that allows me to do is I can equate the s squared terms, and I get an equation that says b plus 1 equals 0. So in one shot, I have that b is equal to negative 1. Okay, and then I kind of have my choice. I can equate 2 plus c plus b to 0, or I see that there's an equation with only one unknown. Right? So the s to the 0 term, I get that 2 plus c equals 1. And in this case, I also get that c is equal to negative 1. Okay, so it's up to you. There are many different ways to do this. I chose to find a first and plug it in. That made the math downstream in the seeding portion a little bit more straightforward, but you could also opt to just jump straight to the seeding method from the get-go. Okay, so now we have all our coefficients, a, b, and c. What do we get to do? Rewrite the original function. That's all we're doing still. Okay, so this is the original S-domain function, but here is a different way to write it, and now I have a, b, and c available. Okay, so we're going to rewrite the original function. A was equal to 1, so that's 1 over s. B and c were minus 1, so I'm just going to factor that out, and I'll get an s plus 1 in the numerator. And all of that is just divided by s squared plus 2s plus 2. Okay, so what I did here, if you can see, is it was b, s plus c. Well, b and c are both equal to negative 1, so I factored out the negative 1, and I was just left with s plus 1 in the numerator. Okay, so this is the original function. This is big F of s. But taking the inverse Laplace of this is trivial, right? I know how to do that. And remember, the whole point of doing partial fraction decomposition is to make the resulting sum of terms simpler so that you can just refer to the Laplace table. Now you might be thinking, uh-oh, what about this guy? Is this actually on the Laplace table? The whole point of doing all of this was to make sure that all these terms exist on the Laplace table. And now I'm in a situation where this kind of looks a little funky, right? But usually when you have a quadratic denominator in one of your terms, if you look at the Laplace table, there are several entries that have quadratic denominators. Okay, so the s squared plus omega squared, s squared minus omega squared, s plus a squared plus omega squared. There's several terms that have quadratic denominators. So this was not all for nothing. We can actually work on this guy a little bit more. In fact, generally when you have a quadratic denominator, the first thing you want to do is to complete the square on the denominator. What that means is to take the middle term 2, divide it by 2, and square it. So 2 over 2 is 1, 1 squared equals 1, and then I'm going to add and subtract that term, plus 1 minus 1. I'm going to add and subtract that term to the denominator so that I can produce a perfect square, right? So let's just work on this guy for a second. We've got s plus 1 over s squared plus 2s plus 2 plus 1 minus 1. It sounds a little bit ridiculous, but if you do complete the square correctly, what that allows you to do is to group some of the terms together. So s squared plus 2s plus 1, that equals a perfect square. So s plus 1 squared. S plus 1 squared is s squared plus 2s plus 1. And then you still have this leftover stuff, so 2 minus 1, which is 1. You can't ignore that, but now this is looking a little bit more promising. Right? It's looking a little bit more promising. And I'm actually going to write 1 squared. I'm going to write this 1 as 1 squared. And the reason I'm going to do that is when we look at the Laplace table. So notice that I've got s plus 1 over s plus 1 squared plus 1 squared. Look at the Laplace table. There is an entry that says s plus a divided by that same s plus a, the quantity squared, plus omega squared. So this is exactly what we wanted. Right? So this term right here is exactly of the form in this entry right here. And so now I can see that the inverse Laplace is just the thing in the left-hand column. It's just e to the minus at cosine of omega t. Okay, so now with a little bit of manipulation, I now know the inverse Laplace of this. And finally, I can get to little f of t is equal to the inverse Laplace of 1 over s is 1 minus, so the minus comes down, and then the inverse Laplace of this is e to the minus at, so a is 1, so e to the minus t cosine of 1t. And that becomes the inverse Laplace of the original S-domain function. Okay, that covers all of your bases. So these 4 cases allow you to take the inverse Laplace of any S-domain function that you can encounter. Okay, so through the process of partial fraction expansion, identifying what case you have, whether it's distinct real roots, repeated real roots, or complex roots, you can figure out which case you're in and take the appropriate action so that you can take the inverse Laplace of any S-domain function and get it back into the time function. All right. These were not fun, right? These were definitely tedious. There's a lot of math involved, but now that we can do both of these things, time domain to S domain and then back to time domain, now we can actually do some interesting things. So one interesting thing you can do with this Laplace method, going back and forth between the time and S domain, is you can actually solve an initial value differential equation problem. It allows you to do that without having to go through the traditional methods that you may have learned in your DiffEq course. Okay, so let me show you how that works. Basically going to solve a differential equation using the Laplace method. So if we want to solve a differential equation, it really comes down to a 2-step process. We're going to jump into the S domain, and in the S domain we're going to handle the initial conditions as well as the forcing functions, and then basically we jump back out into the time domain, and then somehow magically the differential equation is solved. Okay, not magically. I'll show you what I mean. So we want to solve this differential equation, x dot plus 3x is equal to 2, with the initial condition x0 is equal to 1. Okay, so I want to solve that differential equation. Like I said, the process is first, let's jump into the S domain, and that's where we're going to handle the initial condition and forcing function, and then jump back out to the time domain. So jumping into the S domain requires us to take the Laplace transform of both sides of the differential equation. Okay, so just like before, the Laplace transform of x dot, that's going to be s times big X of s minus the initial condition in the time domain. That is the Laplace transform of x dot. The Laplace transform of 3x, well, that's just 3 times big X of s. And then on the right-hand side, we've got the Laplace transform of a constant value 2. remember that the Laplace transform of a constant function of time, a, is a over s. So in this case, the right-hand side of the equation should look like 2 over s. Okay, now I'm going to stop here to highlight a subtle but very critical point, and that's the following. When I took the Laplace transform of 3, that just came straight down into the s domain. So that value got to come down as 3. The 2 became 2 over s. So why is it that the 2 became 2 over s, but the 3 just came down as a constant value? Okay, that's the question that I'm posing to you. The answer has to do with the nature of those two values. Okay, there's a difference between a scalar constant and a constant function of time. That's the key difference here. Okay, so a scalar constant, let me do this first. A scalar constant is nothing more than a point on a number line, right? So you've got a number line 0, 1, 2, 3, right? 0, 1, 2, 3, and so forth. A scalar constant is just a point on a number line. And scalar constants can come down, right? The Laplace of a scalar constant is just that scalar constant. It can just come down. Whereas a constant function of time is not one single value on the timeline. It's actually an infinite number of values that all have the same value, right? So a constant function of time looks like this, right? This is a constant function of time. It's a function which is an infinite number of points that all have the same value, right? Constant functions of time fall under the Laplace table. So the Laplace transform of a constant function of time, you have to use the Laplace transform. It becomes 2 over s. So that's the difference here. Now you may be wondering, well, how do I know if it's a scalar constant or a constant function of time? Generally, I'll tell you, or it'll be clear in the problem statement. But another way to know is that for a differential equation written in this sort of standardized form, the forcing function is always on the right-hand side. So this is a non-homogeneous part of the equation. We call that the forcing function when we refer to it in dynamic systems and control systems. The thing on the right-hand side of the ODE, that's the forcing function. Okay, so things on the right-hand side, even if it's constant, you generally treat that as a constant function of time, which means you have to take the Laplace transform of it. Okay, all other scalar constants can just come down unaffected. Okay, so I hope that clears that up. I know it's a very subtle point, but I know students get tripped up on that a lot, so I figured I'd sort of try and head you off at the pass. Okay, so this nonetheless is the Laplace transform of the differential equation. Now, when we were solving for a transfer function in the very first part of this lecture, we zeroed out all the initial conditions because the definition of a transfer function is Laplace of the output over the Laplace of the input under zero initial conditions. However, we're not solving for a transfer function here. We're not deriving a transfer function, we're solving a differential equation. So we cannot just zero out this initial condition. In fact, we have to input what was given to us. Okay? So this doesn't become 0, it actually becomes 1. And now it changes a little bit, right? We just can't zero that out anymore. So this is what I mean by jump into the S domain. And in the S domain is where we're going to handle the initial condition, right here. And it's also where we're going to handle the forcing function, right? We took the Laplace transform of it. Okay? Once we've taken care of those things, we basically want to solve for big X of S. Okay? So we want to solve for big X of S. That means, let's just clean things up here a little bit. We've got S times X minus 1 plus 3X is equal to 2 over S. So I can group things together a little bit. 3 plus S, S plus 3 times X of S is equal to 2 over S plus 1. We'll move the 1 to the other side. And rather than just divide both sides by S plus 3 first, I'd rather clean this up a little bit. So instead of 1, let's just write this as S over S. and that will allow us to clean up the right-hand side considerably. So it becomes s plus 2 over s. Now dividing both sides by s plus 3, we get that x of s equals s plus 2 over s times s plus 3. Okay, so technically speaking, I said solve the ODE here. Well, this is actually the answer. This is I solved for x, right? It's just I solved for x in the wrong domain. So this is the answer of the ODE in the s domain. But usually when you say solve an ODE, you mean what is x of t? I want little x of t. And all that remains to do is to take the inverse Laplace of this. So take the inverse Laplace of x over s, and I will have my little x of t. Well, how do we take the inverse Laplace of funky s-domain functions? We just went through that, right? So we can identify this as a case 2 scenario because we have distinct real roots. We have s equals 0 and s equals negative 3. We'll do a quick partial fraction expansion, solve for the coefficients, and then take the inverse Laplace of the corresponding simpler terms. Okay, the full work through of that is in the notes, but this is exactly what we did in the previous example. So with confidence, I can say, well, I know how to take the inverse Laplace of this using some partial fraction and probably the cover-up method. I simply find that little x of t is equal to 2/3 plus 1/3 e to the minus 3t. And this is the solution to this initial value differential equation problem. Okay? Solving differential equations using the Laplace method was a game changer for me when I learned it because it applies to any differential equation with any initial conditions and any forcing function you could basically come up with. Okay? It's a very powerful method, and it relies on the Laplace transform. Okay, I'm going to have to start a new sheet here, but I can say with confidence that we now know how to solve differential equations. Okay, so let's get to the last little checkbox here, which is the forced response, and then we will wrap things up with the Laplace transform review here. Okay, I do want to emphasize that the forced response is very important when it comes to dynamic system analysis because, again, it essentially allows you to analytically simulate the response of a system without actually having to apply it to the real life system. That should give me enough room here. Okay, so the forced response. Forced response. Okay, so I've got some dynamic system. I know the input and I want to find the output. Okay, that's the idea. That's the idea. Is I have some real life system and I've modeled it, so I've got the transfer function and I know the input. I just want to figure out what the output is going to be for that particular input. Okay, for this system, we've already modeled the vehicle velocity dynamics, so let's just use that. Starting from where we left off of last lecture, we had that v dot is minus b over m v plus 1 over m u. So basically it's v dot equals minus a constant v plus some other constant times u. So we can plug in some actual values. Let's just keep this example simple. Let's just say it's minus 10v plus 2u. Okay, so we just plugged in some values for b and m, and now we've got this differential equation that is driving the dynamics of that system. Let's also say that u of t is equal to 1. It's a constant value of time. So we get into the car and we apply a constant input. Right? So basically that's just like flooring the gas pedal. And what we want to do is find v. Right? But instead of recalling how to solve this differential equation, I can use the Laplace transform and make things a lot simpler. Okay, so if I take the Laplace transform of both sides of this differential equation, I want to derive the transfer function, so I get that it's SV minus V minus initial condition is equal to minus 10 big V of S plus 2 U of S. And sometimes I will drop the argument because sometimes it's easier to just write capital letters, which implies S domain. versus lowercase letters, which implies time domain. Okay, so because I'm deriving a transfer function, I don't care about the initial condition, and solving for the ratio of v over u, I get the transfer function from u to v of 2 over s plus 10. And one thing to remember is that the input is always the denominator, the output is always the numerator. So you say this is a transfer function from the input u to the output v. Okay, so it's always u to v, so the denominator to the numerator is how you say the transfer function. Okay, but so I've got the transfer function p of s, which represents the transfer function from u to v, and I know the input u of t is equal to 1, which means by taking the Laplace transform of this, I can see that u of s equals 1 over s. And that's a key point to be made here, is that I basically have an equation. It says that p is equal to v over u. I know the plant model is p, and I know the input u. So algebraically, if I solve for v, I get that v is equal to p of s times u of s. That's kind of the entire point of forced response, is that in the Laplace domain, the mathematics are very simple. It's a simple product of p of s times u of s equals the output. And that's what makes the Laplace method so attractive here, is that v of s is now just, so I could plug in 2 over s plus 10, and u of s was equal to 1 over s. Well, this is big V of s in the s domain. If I want to get little v of t in the time domain, I just have to take the inverse Laplace of this product, which I know how to do now, right? Because we went through that sort of tedious review of all those 4 different cases. So I know how to take the inverse Laplace of this. Ends up working out to be 1 over 5 minus 1 over 5 e to the minus 10t. Okay, so the details of that inverse Laplace are in the notes, but again, it's exactly, it's a case 2, distinct real roots, which we went through earlier in the lecture. Okay, so this is what you end up with when you take the inverse Laplace of big V of s, but this is fundamentally how you apply the Laplace method to compute a forced response. Basically, you solve for the output as equal to the plant times the input in the S domain. And from that, those mathematics allow you to compute the analytical form of the output as if you went out to the field and you tested this yourself. Okay? Just to bring things full circle, 1/5 minus 1/5 e to the minus 10t, well, that looks like this. The actual velocity profile looks like this. 1/5, which is some constant value, minus a decaying exponential, well, that looks like exactly the intuitive response to getting into a car and flooring it that we sort of discussed on the first lecture, right? So this is basically just validation of our initial intuition, but now we're using the S domain forced response method instead of relying on our intuition. Okay, so forced response, we're going to see more of this in the coming lectures because it's so valuable to doing dynamic system analysis, in that you can basically predict or compute the output of a dynamic system if you know the plant model and you know the input that you're applying. Okay. Well, we have gone through a lot here. The last thing I want to leave you with is a challenge problem. Okay, so keep in mind that at the end of the day, these are all the things that I want you to be able to do. I need you to be able to confidently check off each one of those boxes and say, I know how to do those things. A benchmark example to test your knowledge of whether or not you can do those things is here. Okay, so I'll pose a problem for you, and if you can solve this problem, then actually you will have inadvertently checked off all of those boxes, right? This problem is actually very tricky, and there's some subtleties here, and if you can kind of muddle through them and understand how this solution works, then you are in great shape. Okay, so I'm going to leave this as a challenge problem for you to solve this differential equation. So this is y double dot plus 4y dot plus 7y is equal to 1. And the initial conditions are y dot of 0 equals 1 and y of 0 equals 0. So solve this. In other words, figure out the particular solution y of t. If you can do that, you're in absolutely great shape. Keep in mind that the thing on the right hand side here, this is a constant function of time. So you'll have to take the Laplace of that when you take the Laplace transform of both sides of the equation. Okay, so I encourage you to work on this. The solution to this example is fully written out in the notes that are available if you're enrolled in the class. But again, if you can do that, then you are exactly where I would like you to be for your understanding of the Laplace transform. Okay, so in the next lecture, we're going to continue our discussion of the system dynamics, but we're going to zoom out a little bit and talk about the system properties. So we're going to step away from the tedious mathematics a little bit, zoom out a little bit, and get a sense for some of the basic fundamental properties of dynamic systems. Okay, so we'll see you in the next one.